Okay. All right. Okay. So what is this mux? What is this mux? So if you guys look at the mux is basically a device, or say you can say a circuit which can actually choose, have, which has many inputs and only one can be chosen to go as output. Okay. So the mux work is to choose the one based on the inputs. Okay, based on the control line. So it has, say for example, simple, say you have got a four tracks in this case, and then the lever, control lever. So they have, kind of, they can decide which one to go out. Okay, so this is a kind of, you can say, kind of, a simple example is kind of, the railway station where, you have many trains which comes and, stops, and then, the controller decides which one to go first and which one to go next, and etc. Okay, so it has actually multiple inputs, and it would be kind of 2 to the power n. Okay, so 2 to the power n, say for example, if your n is 1, that means 2 cross 1 mux. Okay, so a, b, and s. Okay, and now if you say 2 to the power 2, if n is 2, then it is going to be, it's kind of, 4 cross 2, 4 cross 1, and it's two select lines. Okay, so you have got two select lines, say for example S0 and S1, something like this, and then so you have got Z. So it is kind of I0, I1, I2, and I3. Alright, so that is how you can actually choose the mux. Okay, and this mux is used everywhere, on a simple note, in our designs, what is that we do is there is something like, you have got, say, clock. So in a design, right? Say if this is your design, you know what? There would be, something called functional clock. Functional clock. And then there would be a clock that is going to be used for testing purpose. So now what we do is we actually kind of, use this guys. Okay. And then there would be one more signal, which is kind of, see, there is a select line, which is called scan enable. Okay, that is something that we call it like kind of scan enable. Okay, so now this particular thing is going to go to your all the registers. Okay, it is going to go to all the registers. Okay, now this kind of muxing, this is something that people call it like kind of clock muxes. Okay, so people call it like kind of, clock mux. Okay, and this is something that, you will see it everywhere. Okay, you will see it everywhere. Now, not only this, that you might see muxes that is getting used. So now the reason why we have this say clock muxing is because you at any point of time there would be only one logic and one clock that would be reaching these registers. Okay, only one clock that would be reaching these registers. Okay, so you will see mux that is being used everywhere heavily. Okay, and also mux is also kind of treated as a universal gate. Okay, so universal gate. So what is this meaning is you can actually derive any logic using the mux. Okay, now when I say that, what does it mean is, say simple, right? Like you have a mux. Okay, now this is your select line. Yes, Now say this is your Z. Now let's say if you need an inverter, but you have only mux. Okay. Now how do you get this actually? Now say simple. Now when you give S0, okay, when you give S0, now what is that you expect it? You expect it to be say kind of S and Y. So yes, Y, 0, 1. Okay. Now in this case, what is the output that we expect? When you give 0, you are expecting output of 1, and when you give 1, you are expecting output of 0. Now in this case, what is it we do is, so when S is 0, what is that, a value that will go here? So you make it 1 here and 0 here, so that like when S is 0, the 1 would be out. Okay. Because whatever there is here 0, and whatever it is kind of 1. When S is 0, the value of this will come out. Okay. And when S is 1, the value of this will come out. See, basically you are able to bring or make it function like kind of an inverter. Okay. Now for example, let's say you want to make it as a buffer. Now how you do that? So how you can do this actually? So if you look at this particular thing, okay, it is going to be kind of say a mux. Say this is your yes. Now say this is 0. When you give 0, so it is going to be say 0 is going to come out. When you give 1, 1 is going to come out. Okay. So this is going to be your Z. So this operates like kind of a mux, not mux, I mean a buffer. Okay. Now on a simple note, now how do you actually design an AND gate using 2 cross 1 mux? How do you design an AND gate using 2 cross 1 mux? Can you guys give a try? How do you design an AND gate, okay, using 2 cross 1 mux? How can we do this? So what is AND gate equation? Say A, B, and then Y, 0, 0, 0, 1, 1, 0, 1, 1. Okay, now what is the formula? I mean, the output? 0, 0, 0, 1. So now how you decide this here? So here in this case, what is the value? So this A and B are there. When it is 0, irrespective of B value, the output is 0. Okay. So that means you can actually treat that as a I0. Okay. Which is going to be say kind of I0, that is 0. So it is kind of, say it is make it 0, so that it is like kind of say your B, you treat it like kind of B this. Now, what about the other one? The B exactly follows the output. I mean, the output exactly follows the B, okay, in this case. So that means these two are kind of shorted. So B is something over here, and it is something like this. Okay, now you can actually, what you can actually do is, instead of this, you can just say, so this is going to be 0, and then you can actually use it like this is one way of you making it as an AND gate. Any questions here? Okay, now let's go and I'll try to explain what is the content of inside muxes. So now if you look at, right, like as I told, there are different types of muxes that you will have. Okay, so it is basically 2 cross 1, 4 cross 1, and then 8 cross 1 and 16 cross 1. Say it is kind of one select line, and then you have got a two select lines, and then you have got three select lines, and then you have got four select lines. Okay, so these are all, this is how your mux would be. Okay, and now, okay, now, so what is a formula? What is a formula? What is a formula for this? Say, for example, on a simple note, 2 cross 1. Okay, what is going to be the formula? The internal of this, so A, B, and say yes. Now the formula is, it's basically, now you need to write it like kind of yes bar A and then yes B. Okay, yes bar A and then yes B. Okay, this is the formula. Now when you expand this, how it is going to be? So it is going to be two AND gates. Okay, and with one OR gate. So is Y, and then just say this B, and say this is A, and then now you have got yes, that is inverted. Okay, that is basically inverted. So this is how you can actually say, you can implement your logic. So if you look at here, this is yes bar A and this is yes B, and this output is going to be yes bar A plus yes B. You guys are getting? Okay, now let's talk about this 4 cross 1 mux. So how it is going to be? What would be the equation? Can someone try figuring it out? Can someone try figuring it out? 4 cross 1 mux. So try figuring it out. So it is going to be kind of, say, S1, S0. Now A comes out in case of both of them are 0. B, C, D. So it is going to be Y. So it is, the truth table is going to be say, S1, S0. Now, so this is Y. So what it is going to be? 0, 0, 0, 1, 1, 0, 1, 1. Now, say this, in this case, when both of them are 0, 0, it is, this is going to be kind of, A is going to come out, and then in this case, B is going to come out, and in this case, C is going to come out, and D is going to come out. Can you guys write the formula quickly? Can you guys write the formula quickly and draw a picture and send it? So the time that I'm giving you for this is actually 4 minutes max. So I want you to ping in my WhatsApp with this picture. Okay. Try writing it, take a photo and send it across. So we will create the Telegram group maybe sometime this week. Then I will add you guys. Okay. So try writing this and picture. I want you to write the equation and then picture something like this. It's a classwork, not a homework. It's a classwork. Okay, so it is going to be, say for example, in this case, y is equal to s0, s1 whole bar, then a plus s1, s0. Okay, Let me just write it this way. So this is going to be S0, S1, and then B, and then S1, S0. This is going to be the one. Okay, so this S1 and S0 bar, and then C, and then plus S1, S0, D. So this is going to be the the equation that you would probably try to solve it when you write this. Okay, now the diagram is going to be say something like this. Okay, so you have AB, which is basically S0 and S1, and you actually kind of something like this. Okay, uh, the reason why I'm trying to make you guys work is you get used to it, like okay, when there is a mux, okay, that is an internal circuitry. Okay, so you might have covered digital long time back. I'm just trying to recollect everything. Okay, all right. Okay, so now we learned the mux internals. Okay, now the next thing is typical written test questions are implement, okay, 4 cross 1 mux using 2 cross 1 mux. So how do you do this? How do you do this? Say what I need is basically I need 4 cross 1. Okay, but unfortunately I have only the 2 cross 1s with me in my library. Okay, unfortunately, so you can say kind of I have only 2 cross 1s available in my library. Okay, so now how you go and design this? How do you implement this? Okay, so how do we do this? So assuming it is like kind of, so they both have the same thing. Now you can actually implement it like kind of 2 2 and then another one more which is kind of 2. Okay, say now S0 S, basically S0, and then say S1. Okay, now when you say 0, S0, what is this meaning? Let me just remove this particular thing. Okay, now what was the diagram that we have? It was like kind of S1 S0 and then say Y, which is going to be Y. It's kind of when say 0 0 0 1 1 0 1 1. Okay, now say this is going to be kind of A, B, say C and D. Okay, so on a simple note, it is going to be say kind of these two. Okay, S zeros. Say these two are S zeros. So that means when you say S0, it is going to be say A, and then write this B here, and then C here, and then D here. Now, when you say S1, okay, when it is 0, okay, whatever the first mux output will go as a input, and then that would actually come out. So now try to apply here and see if you are able to understand this. You are able to realize the same thing using this 2 cross 1. Can you guys tell me when I give 0 0 in this case, what is it going to come out? Okay, when I give 1 1, okay. Now let me give you a small homework. Implement, okay, 8 cross 1 mux using 2 cross 1. Okay, now my question is, so how many 2 cross 1 you need? how many 2 cross 1 mugs you actually need. How many 2 cross 1 mugs you actually need. Okay, so how is it? How are you saying it's 7? Okay. Okay, can you please draw it with 7 and share the pictures in WhatsApp? Okay. Um, is it done? So, if you guys look at right, the way you can actually, you don't need to implement everything. You need to understand that, the simple method is to say like kind of n minus 1. Okay, so you can say like kind of, or say the way I can say is like the n is nothing but the number of inputs. So n minus 1, 2 cross 1 muxes that you need. And in this case, 8 minus 1, which is going to be say 7 2 cross 1 muxes you need. And then you may come across 16 cross 1 mux implementation using 2 cross 1. Now, how many muxes that we need here? So in this case, we need actually kind of 15 2 cross 1 mux. Okay, that's the basic thing. Okay. Now, so let me ask you this one. The next question is implement 8 cross 1 using, okay, 4 cross 1 and 2 cross 1. Using 4 cross 1 and 2 cross 1. Now, how many muxes you need? How many muxes you need? So, how many 4 cross 1s you need and how many 2 cross 1s you need? I want picture. I haven't got anything. Okay, now if you guys look at 8 cross 1, now you ideally need basically two 4 cross 1, say for example. Now, okay, say something like this. It is going to be all the 8 inputs. Now remember, it depends on how you are defining or creating your truth table. Now if you look at here, S1, which is kind of lost, that is your MSB. Okay, and the first one is basically S0. Okay, so you have to choose your controls accordingly. So it is like kind of S0, S1, S2, something like this. You have to choose where your S0 is going to be your LSB and S2 is going to be your kind of MSB. Okay, so and then looking at that, you need to connect your inputs. Okay, so ideally speaking, you need two 4 cross 1 and one 2 cross 1 mux, something that you really need. All right. Okay, now let me ask you a simple thing. Implement NAND gate using mux. Okay, can you guys try this? Implement NAND gate using mux. Okay, so before that, let's go through the slide once and then we will solve that actually. Okay, now assuming this is your equation that you wanted to implement using mux. Okay, now how many variables are there? There are four variables. Okay, and so when you say four variables, what is this meaning? What is it going to be? It is going to be kind of, say three control. It's kind of say uh, 16 cross 1. Ideally, look at this having kind of, four. Then the possible number of states are say 16. Okay, possible states are so basically 1, 6. Now, this can be implemented using say this kind of, three variable goes as a select line and the last one variable will become one of the inputs. So that is how we can actually implement. Okay, now look at this. Write the truth table. Okay, and then mark, basically write your the table something like this. Say it's kind of I0. Okay, I1, I2, I3, I4, I5, I6, I7. So these are all your inputs. What is that you are going to connect? What value that they are going to connect? Is it some variable or some zero or some one and etc. Now this z bar and z. So now ideally speaking, in this case, it is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's kind of say 16. Now, what is that we are going to do is you just try to come up with a table something like this. Okay, all the inputs and then one variable that you are picking, that is basically a LSB. Okay, now you see here there is a 2 which is having 1, so round it off. Okay, and then 4, round it off, and then 6, round it off, then again 8, round it off, now 9, round it off. Okay, and then again 12, round it off. Now so you have actually kind of rounded it. All right, now what is the value? So now remember, if there are no rounds, write it like kind of 0. Okay, now If there are only one grounds, one of them is covered, that means just write, say this is basically Z bar. Okay, and then this is Z bar. Now this is also Z bar. Now both of them are kind of rounded. It would be kind of say 1. Okay, both of them are kind of rounded. So I would say it is kind of 1. Alright. And both of them are kind of not covered. It says 0. Okay, now imagine in this case, say only one is covered in this. So it is going to be say Z. Something like that. Okay. So this is another way where you can actually kind of say, now ideally speaking, this is going to be 0. Now this is going to be Z bar. This is going to be Z bar. This is going to be Z bar. Now 1, 0, Z bar, and then say 0. And this is going to be kind of say W, X, Y. So that is how you can actually look at. Okay. Is that a cool? Do you guys get it? So this is another way of you implementing using mux. Okay, go ahead. Right. It is just another method that you can actually follow something like this. So these are all kind of different methods where you can actually easily understand that. Okay, how can you solve this? No, I did not. No, hold on, hold on. Where it is two is rounded. So that's what I'm saying. In so what is a possible scenario? So it is kind of two values are there. Okay, first is both are, say you can say both are uncovered. Okay, now the next is one or basically one is covered. Correct, one is covered, and second case is both are covered. Both are covered. So now in case of both are uncovered, the value is 0, and both are, when it is uncovered, when both are covered, value is 1, and when only one is covered, it would be either 0 or Z or Z bar. As simple as that, depending on the location where it is being, where the covering is happening. Yeah. Okay. Yeah. Now, do you guys want to give a try the same method for our implementation NAND gate? Can you guys give a try? Doing it. So it is going to be kind of say NAND gate. The formula is going to be say kind of A, B, and say Y 00011011. So it is going to be 1110. Now if you have to write it, so look at this and mux, which is going to be say kind of I0 I1, and say leave this as it is. We will see like kind of I0 I1. Now take your LSB as the thing. So it is going to be kind of say B bar, say like this, and then it's a kind of 0, 1, and 2, and 3. Okay, now what and all are there? So it is kind of this. this, and then this, all of them are there. So it is going to be kind of, now I0 would be connected to 1, and I1 would be connected to B bar. So as simple as that. So it is the final connections happens, say like this. See, this is kind of 1, and then this is kind of B bar, and this is going to be your B. As simple as that. Okay. No, that is not B. That would be your A. That would be your A. Okay. Is that the same answer? Did you guys send it? Okay. All right. So with this, let's wind up the complete uh, combinational. Okay. Okay. Now we'll take 5 minutes break and then we'll get started with the sequential circuits. Is that okay? I want to cover a couple of more slides where we try to understand the difference, what are the different sequential elements and things, and we will see tomorrow, the next class, registers and counters and all that, and we'll wind up your sequential circuits next week. And today we will just go over the basics of sequential elements, and how do we convert your clock period to frequency to clock period, and etc. And what are the basic things. Okay, we'll take 5 minutes break and then we'll connect again. So the next topic is basically sequential circuits. Okay, so combinational circuits is mean basically it's kind of, it only depends on your inputs. Okay, and purely depends on the present state, whatever the values are in. Okay, now when it comes to sequential circuits, that means there is a storage element that is kind of involved. That is a previous state, okay, or based on the past inputs, this it has kind of state, and depending on that also your output changes. Now that is the main thing here. So sequential circuits meaning it is kind of say your combinational circuits plus your storage element, that is the meaning of it. And remember, your output, it does not depend only on your present inputs, and also it is depends on a past sequence of inputs. That is the main reason why we call this as a storage elements. Okay, storage elements. Okay. Now there are two different types of cells that we usually have it when you say sequential. One is basically a latch, which is called as a level sensitive, and the another one is basically a flip flop, which is edge triggered. Okay, and we use both of them. Okay, in our designs we use both of them. Okay, and you need to learn how a latch operates and how a flip flop operates and everything. Okay, so let's try to understand. But before that, what are the different flops that we have in our designs? In total, what are the different sequential elements that you will have in the in the textbook that you have gone through it. So one is basically SR flop, SR flip flop. Then you have a JK flip flop, okay, and then you have a D flip flop, and then you have a T flip flop. Okay, so these are all the four different flops or registers. We call them as the registers as well. You will have it. Now this particular design, or this particular flop, we use it a lot in design. So this is the only thing that we use. You can say kind of D latch or DFF. These are all these two category are the only things that we use in our designs. So we don't prefer SR, we don't prefer JK, and we don't prefer T and all. So any design that you take, it will have only the D latch and DFFs. Okay, so anything that we will try to learn, or when we get into the the physical design topics, you would actually learn only the DFF based circuits. Okay, okay, now Clock period. So what is the meaning of clock period? So clock period is basically the time interval between the pulses. So it is basically from this launch, say this is from here to this. This is something that we call it like kind of one cycle. Okay, it is something one cycle. Okay, and we have kind of the rise time or probably rise age, and then this is going to be your T on. Okay, that is going to be your T on, and then this is going to be your T off. Okay, so this is going to be your T on and T off. Okay, and this is going to be your T off, and now your duty cycle. Okay, okay, so this is how we calculate the duty cycle. And your homework, what is the duty cycle that we prefer in our designs? So you can have actually duty cycle of 25.25, basically 25%, okay, 50%, and then 75%, which is the one we prefer. Find it out. This is something with respect to your designer's call. Okay, so now let's say if you have a equal rise, equal, pulse. So T on and T off are equal. Now this is 50% duty cycle. Now there is another one. You will have a pulse which is like this. You will have the next pulse like this. So this is 25%. Now you may have a pulse like this. This is going to be a 75%. Now on what basis you decide which pulse that you wanted actually? Try doing some homework. You will get to know. Okay. Now let's talk about the frequency. Okay. Now let's say you have got clock period of say 1 ns. How do you calculate your frequency? The formula is basically 1 by t. Okay, now apply this, and then we need to calculate. Say it's simple, right? Like you guys look at this way. So milliseconds, microseconds, nanoseconds, picoseconds. So this is going to be 10 to the power minus 3. This is going to be 10 to the power minus 6. This is going to be 10 to the power minus 9. And this is going to be 10 to the power minus 12. Okay. Now, there is a next thing. It is a kilohertz. That is basically 10 to the power 3. And then megahertz, 10 to the power 6. Gigahertz, 10 to the power 9. And then terahertz. Okay. 10 to the power 12. All right. Now, how do we convert this? Now, say for example, F is equal to 1 by T, which is T is nothing but 1 by 1 into Ns is nothing but 10 to the power minus 9. Now, when you try to solve this, okay, so it is going to be 1 into 10 to the power 9. This minus 9, when it becomes on the top side, it becomes positive 9. Now, this is going to be 1 gigahertz. Okay, 1 gigahertz. Okay, all right. Now, can you guys try for 500 megahertz? What would be your clock period when you say 500 megahertz? Can you guys try this using these values that I have given here or the way I solved it? Guys, let's not make mathematical mistakes, please. So let's do this calculation. Okay. So now 1 divided by 500 into 10 to the power 6. Now this becomes, say it is kind of 1 divided by zero point 0.5 into 10 to the power 9. Okay. They both are same. Correct. Now I just go one step back. 1 divided by zero point 0.5 is basically 2. This 10 to the power 9 becomes minus 9. Now it is going to be kind of 2ns. Okay, a simple for mathematics. Now the reason why I am giving you this is, in your interview sometimes people would ask all these things. Okay, you want me to help you on with one more time? Okay, okay, all right. Let me just do this. Say simple. Let me take this. So one by, so it's basically now you need to calculate 1 by f. It's basically time period is something you need. What is your frequency? 1 by 500 into 10 to the power 6. Okay, that is 500 megahertz. Agree? 500 megahertz meaning what? 10 to the power 6, so 500 into 10 to the power 6. Now, a simple basic thing, that is going to be zero point 0.5 into 10 to the power 3. Now, this 500 can be written as something like this. Okay, this 500 can be written as something like this, zero point 0.5 into 10 to the power 3 into 10 to the power 6. So, this and this are same. Okay, now 1 divided by zero point 0.5 into 10 to the power 9. Okay, now this is going to be 2 into 10 to the power, this plus 9 becomes minus 9, which is going to be called as a 2ns. Okay, that is a way we do it. Okay, so you guys give a try, taking a different numbers. Okay, okay, I want you guys to give a try that, say simple, your latch. Say for example, if this is your clock. Okay, now you have got the thing like this. Now say this is your clock, and say this is your D, and what's going to be your Q in case of latch. So latch is level sensitive. Now remember, you just have to draw this on time. Okay, and whatever the value is, just follow that as it is. Okay, whatever the value is, just follow that as it is. Now looking at that, now say this is high. Here it is high. Now here it is high to low. Okay, high to low. Now what is that you need to do is, this high you just connect it like this, and then this actually you continue it. Okay, and this zero you continue it. This is how your latch. So anything that is during this positive window, it will be kind of copied over as it is. Okay, and the last state would be carried all the way till your next pulse. Okay, now what about your flop? So flip flop, now they are kind of edge triggered. Whatever is there in that edge, whatever is there in that edge, it would be same. So it is like kind of, say assuming it's 0 and then it is kind of 1 here. Okay, you next is what, there is again 1. So it is kind of all the way goes till here, and next we don't have it. Or let me just do that way. Okay, so that you get an idea. Okay, say here like this, and then okay, now here it is 1, now here it is 0. So It is going all the way till the next thing, and then it becomes 0 and then continues. Okay. And what about your latch? Latch part is going to be kind of, see, it is going to change here and then going to continue. So this is how your, value, how, this is how we can actually draw the waveforms. Okay. So latch is basically a level sensitive, and the flip flop is basically a edge triggered, and whatever during that value, just that would be copied over to your output in case of latch. And when it comes to flip flop, whatever the value at this point when the signal is rising, during, say, assuming these are all positive edge trigger, okay, it would be kind of, copied. The values would be, whatever the value at the time of the edge, it would be kind of copied over to the queue. So any question on this? Any questions? Yeah, right, right. No, see, the other things is basically we look at transparent data. That is the main reason we always use the clock, nothing else. Okay. Okay. Now the next thing is here I have a thing which I want you guys to take it as a homework. I'll share this snap with you guys, and this recording would be posted. I want you guys to, try this at home and then get back. Okay, so now this week assignment is I have given you a couple of questions, and then this is one of that. And then next week, before you come into the class, I want you to come with, say, something called excitation table. Just go through that, what is this excitation table, how it is being used, so that like we will try to design counters and then shift registers, and we'll go through what is that universal shift registers and all that. And then we will actually, wind up the whole digital part, and then we will move to the CMOS basics part. Okay. Okay, all right. So that's all for the day, guys. Let's stop it here. So next week, likely that we will finish this the digital, and then we will get started with mass basics. Okay. See you guys next week. Bye.